So here we've got a pivot point, we've got some sort of beam, and we've got a mass at the end of it. We are applying a force to this mass, and for simplicity's sake, we're going to assume that angle is 90 degrees, and let's give this a name. This is the position R. And because of this force, it's applied a distance R away, it's at 90 degrees, so this force will be pretty capable of rotating this rod with the mass stuck at the end. For simplicity's sake, we're going to assume that this rod does not have a mass of its own, its mass is negligible. So this rod, or this mass, will move along a circular path like that, and we know that at this instant, this rod will have a certain tangential acceleration. Right, because there's a force acting on it. So from Newton's second law, we know that the force acting on this mass must be equals to the mass itself times the tangential acceleration. Right, that's just Newton's second law. Yes, we know there will be a centripetal acceleration as well, but we're not interested in that at this moment. We've got a force in the tangential direction, we've got an acceleration in the tangential direction. Newton's law tells us at this instant that is a relationship between the two. But we can also calculate the torque produced by that force. We know the torque produced by this force will be equals to the force times how far it is applied from the pivot point times the sine of the angle between them, which in this case would be 90 degrees. So this is just going to be equals to F times R. We know what F is. It's just equals to the tangential acceleration times the mass. So we can substitute that in there. So we've got mass times tangential acceleration times R. So that's the torque. We further know that the tangential acceleration is related to the angular acceleration through this formula. Remember angular acceleration? We denote that by alpha. So we can substitute this in here, and we find then that we've got mass times radius squared times angular acceleration, and this, remember, mass times how far away I am from the axis of rotation squared is the moment of inertia times the angular acceleration. So we get almost exactly Newton's second law, but in terms of purely rotational quantities. So we get that the torque produced by the force is equals to the moment of inertia of the body it's acting on times the angular acceleration of that body. And now you can clearly see the role that the moment of inertia plays. So if you've got a large moment of inertia and you've got a given amount of torque, your angular acceleration will be smaller the greater the moment of inertia is going to be. So if you can solve this, you can say torque, therefore over moment of inertia is equals to angular acceleration, like that. So if I've got a certain amount of torque that I apply, the greater the moment of inertia becomes, the smaller the angular acceleration that results. So larger moments of inertia makes it harder for a certain force to rotate a body. Right now, I just quickly want to show you